Hello everyone. In this video, we'll understand how to derive least square estimators of simple linear regression. Before that, let me remind you what is regression. So regression analysis is concerned with estimating and predicting the population mean value of the dependent variable on the basis of the known or fixed values of explanatory variables. So in most practical situations, what we have is a sample of some variable y corresponding to some fixed variable x. Therefore, our task is to estimate the population regression function on the basis of the sample information. For example, we have this population regression function represented by this equation, and this sample regression function is represented by this equation. Our task is to estimate PRF on the basis of SRF. But the thing is, we can get n number of sample regression functions from n number of samples of the same data. In this graph, you can see we have two different SRFs of two different samples of same data, that is weekly consumption expenditure and weekly income. So how do we know which SRF should be considered and which one is best approximation of PRF? A method is there which would help us to determine the best approximation of PRF. Since we know that SRF is just an approximation of the PRF, so we have a method that will make this approximation as close as possible. Or we can say that SRF should be constructed in such a manner that this alpha hat is as close as possible to the true alpha and this beta hat is as close as possible to the true beta. Here alpha hat and beta hat are the estimators of alpha and beta respectively. Remember that an estimator is also known as sample statistic, and it tells how to estimate the population parameter from the information provided by the sample. Similarly, this mu I hat denotes the sample residual term, and it is an estimator of true mu I. So our primary objective in regression analysis is to estimate the population regression function on the basis of sample regression function, right? So generally there are two methods of estimation, ordinary least squares and maximum likelihood. In my video, I am just going to explain the first method, that is ordinary least squares, which we also call it as classical least squares because it is one of the most commonly used methods in estimating relationships in econometrics. Moreover, it is mathematically much simpler than the method of maximum likelihood. So this method of ordinary least squares was given by a German mathematician called Friedrich Gauss, and this method has some really important and attractive statistical properties which I may discuss in the upcoming videos. And because of such properties, this method is one of the most popular methods of regression analysis. So now let's understand this method quickly and let's see the derivation, how we determine the values of alpha hat and beta hat, right? So we can write yi is equal to yi hat plus mu I hat, where yi hat is equal to this term alpha hat plus beta hat xi. This is the observed values of sample and this is the residual values, right? Then we can write this mu I is equal to yi minus yi hat, and just substituting the value of yi hat in this equation will get the residual value like this. I hope this is clear that how we are getting yi minus alpha hat minus beta hat xi. We have just substituted the value of yi hat, that is alpha hat plus beta hat xi, in this equation, and we are getting this equation, right? Now what we are doing here, we are taking the sum of squares on both sides. Now why we are taking the sum of squares on both sides can be seen by this graph. This is a simple graph of a sample regression function. You can see that some of the residuals are above the graph, above this function, and some are below. The values below are taken as negative values and the values above are the positive values. So if we simply take the sum of these residuals, there is a possibility that we get a zero sum of these residuals. So in order to avoid that problem, what we do, we take the square of these residuals and then we add it up, right? So this is what we have done here. We are just taking the square of sum of squares of these residuals, right? So up to here it is clear. We are just putting this value here and we have squared it up and then taken the sum. So here we are applying the least square criteria, in which we are going to minimize this function, this squared residuals, sum of square residuals. We are going to minimize this function. So this criteria would provide us with the unique estimates of alpha and beta that give the smallest possible value of sum of squared residuals. So how we are going to obtain the minimum value? We are going to differentiate it with respect to the estimators and then we'll set the first differentials equal to 0. So here we are firstly differentiating the squared sum of residuals with respect to alpha hat, and then we are differentiating it with respect to beta hat and putting it equal to 0, right? So whenever we are going to minimize or maximize any function, the first derivative, which gives the slope of a function, is always 0, because at that point the differential value or the slope of the function is 0. So here we have done nothing. We are just applying the power rule of differentiation. You can see here mu I square. So putting the value of mu I and squaring it up and differentiating it, we'll get this value. And with simple mathematics and mathematical manipulation, we are getting this equation 1. I hope this is clear. If you know differentiation, this would be very easy for you to calculate, right? What we have done is bringing to here as per this rule of power rule of differentiation, then to the power 2 minus 1, which is 1, then differentiating this bracketed term with respect to alpha hat, and we'll get minus 1. So simply by simple manipulations, taking some terms to the right side, we'll get this equation. So similarly, we'll differentiate this mu I square, sum of mu I square with respect to beta hat, and we'll get this equation 2. Right? Now we have got two equations and two variables. What are the two variables? Xi and Yi. What we are going to estimate from these two equations, beta hat and alpha hat, right? So we have two equations and two estimators, that is alpha hat and beta hat, and given the two equations we can get the two values of alpha hat and beta hat. Now by simple mathematics, solving these two equations by elimination method, what we are doing here, multiplying equation 1 by summation xi and multiplying equation 2 by n. N is the sample size. So when we'll do this and subtract these two equations, we'll see that these two terms will be eliminated and the rest is this in front of you, right? Then by simple manipulations and simple mathematical manipulations, we can get this value beta hat as this. Similarly, if you put this beta hat value in one of these equations, you can get the value of alpha hat also. So this value is known as direct method. Okay, direct method value of beta hat. Now what we'll do, we'll try to simplify this equation by using the concept of deviations. So how we are going to do that? Here we are multiplying and dividing the numerator and denominator by n, right? After doing this, we'll get this n will be cancelled out, right? Here this summation xi upon n and yi upon n will become the mean values of xi and yi respectively, and here also this will become the square mean of x values. You can see here Simply by writing the mean values, you are getting this. X bar represents the mean of xi and y bar represents the mean of yi. So we know deviation is the difference of an observation from its mean value. So small x and small y denotes the deviations, right? So we are writing it like this. Now simply putting these deviated values in place of xi and yi, we'll get this. Substitute these values in place of this, and after this you just have to do simple manipulation. How are you going to do that? Simply open up the brackets and do some plus minus, you will get this equation. Now in this equation you can see that many terms are getting cancelled out. Summation x is equal to 0. Why? Because sum of deviations is always 0. This is basic statistics, you know this. So similarly summation of y is also 0, and here some terms are just cancelling out. Finally we'll get this term, summation xy upon summation x square, and this is the value of beta hat, and which we have obtained by using the deviation process, right? So here we have obtained or derived the slope coefficient or the estimator. Similarly we'll do for alpha hat, which is the intercept coefficient. We have this equation, and simply by taking sum and dividing both sides by n, we'll get this equation, right? You know this is mean of x, this is mean of y. Simply by writing this and taking this to this side and this to this side, you will get this equation, and this is the derived value of intercept coefficient. So the estimators which we have obtained, that is alpha hat and beta hat, are known as the least square estimators because they are derived from the least squares principle. So this was all about the derivation of least square estimators. In my upcoming videos, I'll show you some statistical properties of these estimators, and we'll also discuss about the assumptions of ordinary least square methods. So thank you for watching this video. I hope I have simplified the things for you now, and this has become very easier for you to understand how we actually derive the values of the estimators of linear regression. So thank you so much for watching, and do hit like, comment and share my videos, and don't forget to subscribe the channel.